Okay, previous lecture we looked at turbulent pipe flow and looked at the coefficient of friction and different types of pressure drop for laminar and turbulent flow, and also the effect of roughness. And it gave us an opportunity to start looking at turbulent boundary layers. So we're going to move on to external boundary layers in this lecture, and these are a lot more complicated because they're changing all the way along the surface, and we need ways to handle this as engineers, and I'm going to introduce two thicknesses, displacement and the momentum thickness, and I'll give you an example of what we use the momentum thickness for. Okay, so nice way to get us to external boundary layers is to think about how does an internal boundary layer form. So in the previous lecture we were looking up at this region, in the fully developed region, but this velocity profile has to develop, and effectively it develops because the entrance of a pipe is a bit like an external boundary layer, and the boundary layer develops and it gets bigger and thicker until it meets the boundary layer from the other side, and the shear stress distribution sorts itself out, and we get to this fully developed state. So one of the characteristics of external boundary layers is that nothing is the same, and in particular the shear stress on the wall is not the same, it changes, and only when you get to the fully developed state does nothing change, including the shear stress. Okay, so we're interested in this region today, and also the next lecture as well. Okay, so main structure, which we've seen on a video, is that we have a thin plate, we've got upstream flow coming across the plate, and out here it's the undisturbed free stream flow, and in the boundary layer we've got viscous forces present, and we've got a velocity profile. So it's always a no slip boundary on the surface of the boundary, and the dotted line effectively tells us where there is the edge of the boundary layer. So let's say it's 99% of the free stream velocity, and we know we've got to get from the free stream velocity to zero across this boundary layer. So this gives us an idea that this region here has quite a high shear stress, quite a high rate of change of velocity near the surface, and as the boundary layer thickens, the shear stress goes down, and then you get the transition to turbulence, and then the boundary layer changes shape. So this is sort of the laminar boundary layer shape, and this is a more better approximation of the turbulent boundary layer. And the turbulent stresses change this boundary layer shape. Okay, and so the tricky thing about external boundary layer is wherever you look at it, it's always different. So nothing is the same along an external boundary layer, and this gives us a lot of complications if we want to work out the drag on these kind of surfaces. So just to sort of try and think about the shear stress distribution on an external boundary layer, this is the slide that we had before, and our shear stress distribution drops, comes down to a point, and at a point where the turbulent boundary layer starts, the shear stress rises, and then it starts to get thicker and thicker, and it starts to drop. Okay, so we need to try and deal with this and understand it, and calculate things with it. Okay, so one of the good things about a turbulent boundary layer is that it resists separation. So if you can make your boundary layer turbulent, it will stick to objects as the flow turns. So a classic example is a golf ball. So let's say we've got this ball here and a golf ball, and they're both going the same speed, and they have the same Reynolds number. So the smooth surface has a laminar boundary layer, and it will separate at this point here, and then it generates quite a wide wake, whereas the roughness promotes turbulent boundary layer, and this turbulent boundary layer has more energy, and it stays stuck on the surface for longer, and it doesn't separate until further around, and this generates a thinner wake. And we will see in the next lecture this wake is effectively a drag, and it's called form drag. And golf balls have very little form drag because they have much smaller wakes relative to the smooth sphere, and this is why golf balls have dimples. So how do we handle dealing with these complicated things as an engineer? So we have two things. One is called a displacement thickness, and one is called the momentum thickness. So conceptually, what we say with, say, the displacement thickness, we say let's say we wanted to do a flow calculation, and we wanted to assume the flow is inviscid and not have this viscous boundary layer around it. How could we do that? Well, so we could calculate, this is our inviscid flow, and if we made our surface slightly, or made our object slightly bigger, so it moved into the flow a little bit, such that this mass defect here and this area here are the same, then we can do an inviscid flow calculation, and this kind of area or mass defect can account for the fact of the mass flow not in this due to the viscosity. So this is what the displacement thickness is called. This doesn't have a great deal of practical use, but the momentum thickness has a much more use because you can calculate the drag with it. Okay, so let's have a look at how you calculate or how you define the displacement and the momentum thicknesses. So the definition is this integral here. So what this integral says, this is the integral from y equals 0 up to y equals infinity of u infinity minus u. So u infinity is the free stream velocity, and this u here, this is the velocity at any point y. Okay, and so u infinity minus u is effectively the length of this dashed line, and so the mass flow of that dashed line of width delta y, density rho, is the mass flow of this little bit. And then if you integrate all of these dy's, you end up with this integral here. Okay, and the definition is that says, well, this has got to be equal to u infinity times this displacement distance times density. So this is the mass flow per unit width of this, and this delta star is defined such that the area inside this hatched thing and this hatched area is the same. Okay, and the definition for the displacement thickness is just this thing rearranged, and it ends up being like this. Okay, so that's the principle of it. The momentum defect is slightly similar, and effectively it says, well, if this wasn't u infinity but u squared, you could work out the momentum defect by this. So this would be effectively this u infinity minus u is the same thing that we've got here, and what we're saying here is the amount of momentum in this bit, this shaded bit, is the same as the amount of momentum in this bit, and this isn't delta but it's this theta. Okay, so this is the momentum defect in the boundary layer. If it was inviscid, this is the difference between the inviscid momentum and the real momentum. Okay, and that's what's defined here, and this allows us to define this momentum thickness to be this. Okay, so the way we use these is we find these integrals in calculations, and then we say, that's just theta. Okay, and you can define the ratio of these two things. It's called a shape factor, h, and effectively it's the shape of the velocity profile. If you work it out for a laminar boundary layer, you can work it out to be about 2.6, and if it's a turbulent boundary layer, it's somewhere between 1.3 and 1.6. Okay, and the usefulness is the fact that the drag is simply this. It's the momentum defect of the boundary layer, which makes some sense. And this is much easier to use than doing this rather unpleasant integral. Okay, so let's try and do this using an example. So what we've got here is we've got a plate, free stream flow up here, and we draw a control volume along this, like this. And it's a uniform flow in here. We've got a boundary layer coming out of here with a velocity profile, and this line up here is a streamline, and this streamline is outside the boundary layer. So we only know that we know that there's one mass and momentum flow going in, and there's one mass and momentum flow coming out. So we can write mass conservation. We can say that the mass coming in is this, so per unit width. So this is the area per unit width. This is the velocity coming into the control volume here, and this is the height of that. And we don't know what the velocity profile is, but if we wanted to work out the mass flow, we could work it out if we knew what u was in terms of y. Okay, so this is the mass flow out. And we can write momentum conservation. So we've got the momentum out, which is this term, minus the momentum in, which is this, and we've got the drag. So this is the actual drag, not the drag on the control volume. So we've got a minus there. Okay, so I said in the previous slide that this is the case. So show that this is true. That would be the question. Okay, so what we do is these are our two equations that we got from the previous slide. Okay, so the first step is we substitute the mass conservation equation into momentum conservation. So what we're doing here is we're taking this term of the momentum conservation and saying actually that's just rho u times this this thing is rho u infinity times h1, and rho u infinity h1 is actually this. So effectively you can substitute this term into here and you can end up with this term here. And then the next step is to divide everything by rho u infinity squared. So we've got the drag, which is this, and then we've got this term divided by u infinity squared, so that ends up being here, and then we've got a u infinity and a u. If that's divided by u infinity, we end up with this ratio here. And then we say, I recognize this. This is my definition for momentum thickness. So therefore, this must all be true. And we can also relate the momentum thickness to the wall shear stress, because we know that the drag is actually the wall shear stress multiplied by the area. So that's for a small element here, and this allows us to relate the change in the momentum thickness with the drag per unit length, or the wall shear stress, and we can see that the momentum defect, if you like, the rate of change of momentum defect with x, is actually the friction coefficient. So we saw this when we looked at pipe flow. So this hooks into the previous lecture, where what we're doing now is we're relating the momentum thickness along the external boundary layer to the wall shear stress and the friction coefficient. So that is quite useful for us. Okay, so main thing about the lecture is we've introduced mass and momentum thicknesses, and had an example of how to work out wall shear stress and friction drag, and briefly touched on separation, which comes more in the next lecture.